Hello friends, welcome to the course Multivariate Procedures with R. You can recall that in the last lecture we had talked about the normal distribution. First we discussed the theoretical properties, and then in the last lecture we had seen its implementation in the R software. But in case if you want to extend it to more than one variable, that means from univariate to say bivariate normal, or in case if you have more than two random variables, then multivariate normal, then how to get it done. And as we have discussed many times that in real life most of the real data is multivariate, and there we will need the assumptions of multivariate normal. So my objective in this lecture and in the past two lectures was to begin with a univariate normal, give you a fair idea how are you going to do it, and then now finally extend it to a multivariate setup. So this is what I am going to do in this lecture now. I am assuming that you have understood the univariate normal distribution properly, and based on that I will try to give you the probability density function of bivariate normal distribution, and there I will try to show you that how the number of parameters get increased. For example, in the case of univariate normal distribution you have only two parameters, mean and variance, but now in the case of the bivariate you have two variables. So for each variable you have mean variance, that means 4 parameters, but there is one more, that is the interaction between the two variable x and y, that is the joint effect of the random variable, that also has to be incorporated. So that can be incorporated through how? If you recall, we had discussed the concept of covariance, correlation coefficient. So now one parameter related to either covariance or correlation coefficient will also get introduced. Now in case if you extend it to a multivariate setup, then each of the variable will have its mean, variance as well as their joint variations. They will come into existence. So this is how we are going to learn this lecture. But before starting the lecture, I would like to clarify this bivariate normal and multivariate normal. I am going to discuss here only their properties, but they have a very strong mathematical background. And in the course of multivariate analysis, we try to give all type of mathematical derivation that how to obtain those things, like as marginal distribution, conditional distribution, their mean, their variances, etc. But here I am not going to do it. My objective is this: I am trying to do here the multivariate analysis, only that much amount which I require in the lectures in future. So let us begin this lecture and try to understand about bivariate normal, multivariate normal along with their application in the R software. So let us begin our lecture. So now if you try to recall, we had considered the univariate normal, say x following normal mu sigma square, and its probability density function say is given as 1 over sigma root 2 pi exponential of here minus 1 over 2 x minus mu upon sigma whole square, right? Where this x and mu they lie between minus infinity and plus infinity, and sigma square is greater than 0. And both mu and sigma square, they are the parameters. So parameters are those things, if you know them, then you know the complete details about the probability distribution. So now we try to extend it to a bivariate case. That means there are two variables. Suppose I can say here there is another variable here y, which is following here normal mu sigma square. They may have same mean, different mean, but now we also want that we want to consider their joint effect, right? So now the extension of a normal distribution to two random variable is bivariate normal distribution. And the probability density function of a bivariate normal distribution is given here like this, that there are two random variables x and y. So we have here now the parameters here sigma x, sigma y, mu x, mu y, and rho, and it is given here like this. It looks like normal, but it is different because there are a couple of things more. So because there is here one parameter here which is rho. So as you have learned that mu indicates the mean, sigma square indicates the variance. Similarly, rho indicates the correlation coefficient. This I will try to show you later, but this is how the joint effect enters into the normal distribution. So this PDF is given by 1 upon 2 pi sigma x c y sigma y square root of 1 minus rho square exponential of minus 1 upon 2 1 minus rho square x minus mu x whole square upon sigma x square y minus mu y whole square upon sigma y square minus twice of rho x minus mu x y minus mu y divided by sigma x sigma y. Right, where x and y both lies between minus infinity and plus infinity, mu x mu y, they are also lying between minus infinity and plus infinity. And you can see here the parameters here are mu x, mu y, sigma x, sigma y, and here rho. Right. So sigma x and sigma y square, they are lying between 0 and infinity, and rho is the correlation coefficient, so it is lying between minus 1 and plus 1. So this is how we try to define this bivariate normal distribution function. Now I'm giving you a small exercise. Try to substitute here rho is equal to 0 and then try to see what happens. Whatever you will get, that you can see this f of xy, this can be represented here as say f of x and f of y. Please try to do it yourself. And if you recall what this means, that is indicating that the two random variables x and y are independent. And if you try to recall, when we understood the concept of stochastic independence, then we had seen that if you want to judge whether two random variables are stochastically independent of each other, then we have to check whether their joint density function fxy can be expressed as their marginal density function fx into fy. So if you try to see if rho becomes 0, that means they are independent, and this joint density function can be expressed as the product of marginal of x and marginal of y, which are univariate normal distribution. But anyway, this is only for your exercise. Now, in this bivariate normal distribution, in case if I try to find out the marginal distributions, well, you know how to find out them. F of x will be minus infinity to infinity f of xy dy. And if you try to solve it, this will come out to be normal mu x sigma x square. And similarly, if you try to find out the marginal density of y, this will come out to be here normal distribution with mean mu y and variance sigma y square. And yeah, similarly you can find out the conditional distribution also, like as f of x given y and f of y given x. Anyway, I will try to handle it in the multivariate case. I will show you. Right. This I am trying to give you only some idea how can you extend the concept of univariate into say bivariate and then to multivariate. Now you can see here, if I try to find out here the covariance between x and y, in this case this will come out to be rho into sigma x into sigma y. So in case if you try to find out the correlation coefficient in the case of bivariate normal distribution, this can be obtained as a covariance of xy divided by square root of variance of x and variance of y, that is standard deviation of x and standard deviation of y. That is the same definition, if you recall, we had done earlier when we were trying to do the concepts in descriptive statistics. So now this covariance of xy can be written here as a rho into sigma x sigma y, and in the denominator these are the standard deviation sigma x sigma y, both get cancelled, and this comes out to be here rho. So now if you try to see, earlier we didn't knew what is rho, but now we have seen that rho is representing the correlation coefficient, right? And in case if rho is equal to here 0, then you can verify that f of xy can be expressed as the product of f of x and f of y, right? So this x and y are independent. Now the same concept will be extended to a multivariate case also. So now let us try to extend this bivariate case to a multivariate case where we are considering that there are p random variables. something like x1, x2, xp. Now these p random variables can be expressed in the form of a random vector. Vector is the vector of vectors and matrices. So I try to express this p variables x1, x2, xp here as a x underscore, which is here like this, right? And the space of x is going to be the set of n tuples. Now let me try to show you here that in case if I say that x follows normal mu sigma, then what are the changes? Well, I am going pretty slow because I am not giving you the mathematical details, but I want to explain you, right? So now you can see here mu here is a mean vector, which is here like this, right? And what is here? Sigma. In the case of bivariate, you can extend this covariance matrix as say here sigma x square, sigma y square, and here say covariance between x and y, which is rho sigma x sigma y, like this, right? This is indicated here as a sigma xy. So this covariance matrix can be written here as a sigma x square, sigma y square, sigma xy, sigma yx. Now I try to extend it to a multivariate case. The covariance matrix here sigma can be expressed here as a sigma 1 square, which is the variance of x1. Then first you try to look at the diagonal elements. This is sigma 2 square, which is the variance of x2. Then we have here variance of xp, sigma square p. Now on the off diagonal elements, we are trying to consider here the covariances. So sigma 1 2 is the covariance between x1 and x2. Sigma 1 3 is the covariance between x1 and x3, and sigma 1p is the covariance between x1 and xp. And similarly, if you try to consider the second row, sigma 2 3 is the covariance between x2 and x3, and similarly here sigma 2p is the covariance between x2 and xp, right? And definitely because you know that the covariance between x, y is the same as covariance between y and x, right? So the lower diagonal elements like this one, this is going to be the same as the upper diagonal elements. That means sigma 1 2 will be the same as sigma 2 1, sigma 1 3 will be equal to the same as sigma 3 1, and so on. So this is how we try to create the sigma matrix. Now in case if you want to write down the probability density function of this normal p, this I can write down here as say 1 over 2 pi raised to power here p by 2, determinant of sigma raised to power of 1 by 2, exponential of minus 1 over 2 x minus mu transpose sigma inverse x minus mu, like this, right? This is the PDF of multivariate normal distribution of a random vector x, which is of order p cross 1. Well, you can find these expressions in the book, that's not a big deal, right? And there is a proper proof and derivation that how you obtain such a thing. But anyway, I am not going into that correction. So this is about this is how this multivariate normal distribution is given. Now what I try to do is the following, means I try to clear here this writing so that I can show you it here more clearly. Now I try to partition it into two subvectors. You can see here now I am writing in the blue color, so you simply have to look into the blue color. So x is now being partitioned into two variables, subvectors x1 and x2. It is here like this. You can see here that if I try to remove this thing, and it is something like this, somewhere I am trying to write this, say x1 here, say here I can write down here say xq, and then after that xq plus 1 up to here xp. right, like this, x1, x2, xq, xq plus 1 up to xq plus 2 up to here xp, and then I try to divide it here. So this is your here x1 subvector and this is your here x2 subvector. So this is what I am trying to do here. Now once you try to do this type of division, then your mean vector and covariance matrix, they have to be suitably partitioned. So I am assuming here that the x1 subvector has a order q cross 1, and this x2 vector is going to be of order p minus q, right? And now, so you try to partition this mu here like this, somewhere here. And similarly, this covariance matrix will also be partitioned. All the variables in the subvector x1, that means x1, x2, xq, they will be here like this. So the covariance matrix of the subvector x1 will be here like this. This is the covariance matrix of x1. The covariance matrix of the subvector x2, this will be your here like this. And this is here the covariance between the subvectors x1 and x2. And this is here the covariance between subvector x bar 2 and x bar 1. Right. Now, what will be the order of sigma 11? Sigma 11 has q elements, so its order will be q by q. Sigma 22 is based on x bar x underscore 2 subvector, which has p minus q elements, so the order of the sigma 22 will be p minus q. And similarly, this sigma 12 will be q into p minus q. Now, as we had seen earlier that in the case of univariate normal distribution, that mu was the mean and sigma square was the variance. Similarly, in the case of multivariate normal distribution, this mean vector mu actually is the mean vector. So you can see this is a direct extension of the univariate case to a multivariate case. And sigma is here the covariance matrix of here x, right? So you can also see that this is also a sort of extension of the bivariate normal distribution to multivariate. In the case of bivariate, there was only one off diagonal element sigma xy, but now you have pairwise covariances for all the variables. Now this sigma is a matrix, so we have to assume that it is a positive definite matrix. It is non-singular and it is a symmetric matrix. Non-singular, you know that the determinant of the sigma is not equal to 0, and symmetric means that the diagonal and off diagonal elements are the same. And positive definite means if you try to take a quadratic form, something like x transpose sigma x, then this is going to be greater than 0. Well, I am not going into the details of this definition because I believe that you are aware of these concepts from the matrix theory. But symbolically, we write this positive definite as sigma greater than 0. So wherever I simply write this matrix greater than 0, this indicates that the sigma or that matrix is assumed to be a positive definite matrix. Now, as you had found the marginal distributions in the case of bivariate normal distribution, similarly in the case of multivariate normal distribution, you can also find out the marginal distribution. I am not going to give you here the proof or derivation, but I am simply showing you here the direct result, that in case if you try to recall that in the case of bivariate normal, this fxy had a marginal fx and fy, and fx was normal mu x sigma x square and fy was normal mu y sigma y square. So in the case of multivariate normal distribution, the same thing extends, that each of xi will have a normal mu I sigma I square, right, for each I goes from 1 to p, right. Now similarly, if you try to look at these random subvectors, say x1 underscore and x2 underscore, the marginal distribution of these subvectors are found to be normal. The order here is q, and the mean vector here is mu1 and covariance matrix sigma 1 1. And similarly, in the case of x2, this is normal p minus q, that is the dimension of the multivariate normal distribution, and its mean vector is mu2 and covariance matrix here is sigma 2 2. So, you can see here whatever you had done in the case of bivariate normal, that if you have ff xy, then the marginals are say univariate normal. So, now the same thing is happening here, that if you try to create here two submatrices, then the submatrices are also distributed as multivariate normal, and their mean vector and covariance matrix, they are suitably divided. Now, similarly, if you try to find out the conditional distributions, you can recall that when we did this concept, we had denoted the x given y equal to y, right, here like this. It was something like here f of xy, and then it was the marginal of here y, and so on. So, the similar concept is used here in the case of subvectors also, and if I try to consider here the same setup, that x has been partitioned into two subvectors x1 and x2, then the conditional distribution of x1 given x2, it is here obtained here like this. Multivariate normal distribution, the order of the distribution here is q, and the mean vector here is mu1, but it has one more term, mu1 plus sigma 1 2 sigma 2 2 inverse x2 minus mu2, right. And you can see here, because it is conditional, so this x2 is actually here known, and the covariance matrix is coming out to be in this format, sigma 1 1 minus sigma 1 2 sigma 2 2 inverse sigma 2 1. In many books you will find that there is a standard notation for this expression. It is sigma 1 1 dot 2. So, the way it is written, it is something like this. Suppose if I write here sigma 1 1 dot 2, so first you have to write sigma 1 1, then you have to write minus, and then you have to write this sigma 1 2 sigma 1 2 once again. So, what we try to do here, I try to write down here sigma 1 2, because the order has to match with the sigma 1 1, because sigma 1 1, this is sigma 1 2, now there is here sigma 2 2 inverse, because the orders have to match, and then it has to be here sigma 2 1, so that the orders match here. So, this is how this symbol is given. So, but you can see here that this new mean vector, this can be called here as say mu1 star, and anyway this covariance matrix is already renamed as sigma 1 1 dot 2. So, you can see here that the conditional distribution of the subvector x1 given another subvector x2 is again a multivariate normal distribution with certain mean vector and certain covariance matrices. And the same thing happens when you try to consider the conditional distribution of x2 given x1. So, this comes out to be here, the mean vector here is mu2 plus sigma 2 1 sigma 1 1 whole inverse x1 minus mu1. Actually, this can be just obtained just by interchanging the 1 and 2 here and here, right. And similarly, if you try to see, the covariance matrix will come out to be here like this. Now, if I ask you how can you express this covariance matrix in the symbol like you have used here sigma 1 1 dot 2, you can see here this can be written as here sigma 2 2 dot 1. So, that is a standard symbol. So, now you can see here, if I try to write down this mean vector here as say mu2 star, then once again I can say that the conditional distribution of subvector x2 given subvector x1 is again multivariate normal distribution with mean vector mu2 star and covariance matrix sigma 2 2 dot 1. So, these type of different probability distributions can be found without any problem. Now, let us try to understand that how are we going to work in the R software with this multivariate normal distribution. Now, you can see that bivariate normal distribution is also a particular case of multivariate normal, right, and even including the univariate also. In order to understand or implement the multivariate normal distribution in the R, exactly in the same way as we had considered in the case of univariate normal. But in univariate normal, we don't need any additional package, and that is available in the base package. But for multivariate normal distribution, you need to have here another package, which is MVT-NORM, MVT norm. So you need to install this package first by using the command install.packages, and within parentheses, within double quotes, MVT norm, and then you have to load this library MVT norm. So this function provides the density function and a random number generator for the multivariate normal distribution with mean equal to, like as here, mean, and covariance matrix is equal to sigma. Right. So this is what you have to write down here. For example, you remember that in the case of univariate normal density function, you had used the command like dnorm, which was used to create density, and rnorm to create the random numbers, to generate the random numbers. Similarly, here also we have the command here dmv norm. Then here this the values of the x data vector, what you want, and then here the mean. For example, you can give it anything here, but just to be on the safe side, it is saying rep 0 to p. That means you try to repeat 0 p times. And sigma is the diagonal matrix you can see here. Well, you can choose it anything, whatever you want, but just for the sake of simplicity, I am trying to take it here sigma 1, sigma 2, sigma p. Right. And if you want to generate the random numbers from the multivariate normal, then you have to use the command here RMV NORM, RMV norm. And then N here is the number of data vector that you want to generate. And again, this mean here is given like this, sigma here is given here like this, right? Anyway, these are your choice actually, because you need to define the mean vector and covariance matrix, and you already have learnt in the topic of matrices theory that how can you write different types of matrices in the R software. So the same thing you have to use here. Anyway, so these are the options which I just explained you. X is the vector of matrices of quantiles, N is the number of observations, mean is the mean vector, and sigma is the covariance matrix. And the default sigma is taken here as a diagonal matrix of the N call X. N call you recall, it was the number of columns in the matrix X, which is P actually in our case, right? And mean vector also, this is here length N call X. That means whatever is the number of columns. If you have x1, x2, xp, p random variable, then your mean vector has mu1, mu2, mu p. Right. Now let me try to give you here some example. Well, so first I try to load this library using the command library mvt norm. Then suppose I try to generate here 2 data vectors. Well, I am not taking here a large number of data vector because of the limitation of the space on my slides. Otherwise, the font size will become very small, and then it will be difficult for you to understand and follow. So I try to use here the command rmv norm. N is equal to 2. That means I want to have 2 data vectors, and I want that this data vector x and y is like normal, bivariate normal, with mean vector here 10 and 20. So I am giving here mean is equal to C 10, 20. And the covariance matrix I want here, this is a diagonal matrix here, like as here 2, 3, and here 0, 0. And once I try to generate this thing, you can see here that this type of observation is produced. Now, how to interpret it? Now, if you try to see every this column, well, there are going to be total 4 number of values. Why? Because 2 random numbers on 2 variables each, right? So you can see here every this here row that is going to express 1 random number. So you want here 2 sets of random number from bivariate normal. So there are going to be here 2 rows which are indicating the observation. For example, this observation is on, say here x, this observation is on y in the first data vector, and in the second data vector this is the observation on here x, and this observation is on y. Now I try to repeat the same thing for by generating the 5 observations. So I simply have to change here n equal to 5, and remaining parameter I make the same, so that there is no confusion. So you can see here 1, 2, 3, 4, and here 5. These 5 sets of data vectors, they are generated, right? And this is here the screenshot of the same operation. But now let me try to show you these things on the R console also, so that you get convinced, right? So I try to now load this library here. I already have installed this package on my computer, so you can see it very easily here. And now I try to say here, use this command here and Control C, and then you can see here it is here like this, right? So now you have got here 2 sets of random numbers. Well, they will not match with the numbers on my slide because they are random, and every time you generate they will give you a different value. Similarly, if you try to change here the number you want to generate, suppose you want to generate here 10 numbers. So you can see here that now there are here means 10 rows. Now suppose if you want to generate here some random numbers from this 4 cross 1 data vector. Suppose I try to make now the mean vector as 10, 20, 30, 40, and suppose I try to make the diagonal matrix also of 4 by 4. So now you can see here, suppose if I make it here, it will come out to be here like this. So now there are here 4 observations on the first data vector, 4 observation on the second data vector, 4 observation on the third data vector, and similarly 4 observation on the 10th data vector. And if you try to repeat it here, you can see here the values will be different. You will not get the same value. Well, if you get that, means the concept of random is violated. Right. So now we come to an end to this lecture, and you can see here what we have now done. We wanted to reach to this multivariate normal distribution. But I believe if I give you it here directly, then it will become little bit complicated for you to understand. That is why I have taken a little bit longer route. But definitely we are going to use each and everything. We have considered the univariate normal distribution. So you will see later on that we are going to use it. And finally, we have come to the multivariate normal distribution, and definitely we are going to use it in the further lectures. Well, I would like to address once again that I have considered only the normal distribution here, but there are many univariate distribution, multivariate distributions which I have not considered here. But in case if you wish, there are books on multivariate distribution where they try to compile different probability, density function, probability mass functions. And also we have not done any mathematical proof because this is not the objective of this course, but we are trying to do it because these things are going to create a foundation for the topics which we are going to handle in the future. For example, you can see here now I am using the concept like matrix, diagonal, which I had given in the earlier lectures. So now I would say that you please try to understand this concept. Try to write down the subvectors and submatrices yourself with the appropriate order. Whenever you are trying to deal with the multivariate analysis with vectors and matrices, one common problem is which occurs including in the programming, that is the order of the vectors and matrices. So that you have to learn how to give it properly, correctly, because only then the R will understand it. But your concept should be clear that why you are giving Q by Q or P minus Q by Q. And then I have given you here the result, but if you have a good background in mathematical statistics, you can go through with the books and try to find out that how these expressions have been found. And then try to see how you can express them in the multivariate normal in R. One more important point to understand. I have shown you in the R software only the multivariate normal distribution with some mean vector mu and covariance matrix sigma. I have not considered here marginal distributions or conditional distribution, and the question comes, how are you going to generate the random numbers for them? Well, that is pretty straightforward. If you try to see, the marginal distributions are again multivariate normal. You simply have to change your mean vector and covariance matrices. And similarly, in the case of conditional distributions, you have to change only the mean vector and covariance matrix. Instead of mu, for example, we have used the symbol mu star, say mu1 star or mu2 star. And instead of covariance matrix sigma, you have to use sigma 11.2 or sigma 22.1. And they themselves are proper matrices. So there is absolutely no issue. Wherever you want, whenever you need, you can generate the random numbers on the marginal as well as conditional distributions. And this is what you have to keep in mind. So I request you that you try to take some example, practice them, be comfortable with these commands, and try to understand what R is trying to do with the multivariate normal distribution. So you practice, and I will see you in the next lecture with more topics. Till then, goodbye.